Hi, this is day 42, and today's episode is brought to you by the Greek letter Phi, which is used to represent magnetic flux, something we might actually be touching on in a little while. For now, though, we want to do a quick example using Ohm's law. Ohm's law was what the lab yesterday dealt with, and you remember if you have a resistor and there's some potential decrease or some voltage drop across the resistor and some current through the resistor, well, these three things, they are related by that equation right there. The voltage drop across the resistor is equal to the current through the resistor times the resistance itself. That right there is Ohm's law. And let's do a simple little problem involving Ohm's law. Here it is. It says a 3 ohm resistor is connected to a 10 volt source. Find the current leaving A, the source, B, the resistor. Okay. First of all, before we jump into the problem, let's talk about the difference between a resistance and a resistor, because I know sometimes I use the term resistance, sometimes I use the term resistor. It's like they're almost interchangeable, like they almost mean the same thing, but not really. Here is the difference between them. A resistance, and we've talked about this before, it's a load that converts electrical energy to heat, like for example a light bulb, a stove element, a soldering iron. A resistor is a specific type of resistance. A resistor is one of these things, okay? Like was used in the lab yesterday. They are used in various circuits. Okay, so don't have to worry about that anymore. Again, I use these two terms interchangeably. Maybe I shouldn't, but I know sometimes I do, but now you know really what's what. Anyway, back to the question here. So yeah, like it says, we've got a 10 volt source. So here's our 10 volt source. So that means there's a potential increase of 10 volts across that source. And here's our 3 ohm resistor. Okay, and we want to find the current leaving the source. So remember, electrons, the way they would move around the circuit would be like this, right? Repelled by the negative terminal of the source, attracted to the positive terminal. The direction of the current, though, if positives could move, they would go like so. If positives could move, they would be repelled by the positive terminal of the source, attracted to the negative terminal of the source. And we need the current leaving the source and also the current over here leaving the resistor. And of course, the first thing you have to realize is that both these currents are the same. It's kind of like a water pipe, remember? But instead of water flow, you're talking about electron flow. And if it were a water pipe, well, you know, however much water is flowing through the pipe here, well, the same amount of water is flowing through the pipe everywhere. So the current is the same everywhere. So that's kind of nice to know. Instead of having to figuring out two things, we just have to figure out one thing. So we can do A and B in one fell swoop. Okay, so how can we do this? Well, remember, the potential increase across a source is going to equal the potential decrease across the load. In any circuit, the potential increase is equal to the potential decrease. 10 volt potential increase here, that means 10 volt potential decrease here. Okay, and what do we have here? Well, here we have a resistor. We know for a resistor, Ohm's law, right? the potential decrease, which is equal to 10 volts, is equal to the current through the resistor. Well, that's what we're interested in, right? We want to figure out the current through the resistor. And then you got to multiply by the resistance itself, which is 3 ohms. So you solve this equation, the 3 slides underneath the 10. And there you go. Don't forget your units. You're talking current. That's measured in coulombs per second or amperes. Done. Piece of cake. Okay, that was pretty easy. To challenge you, we're going to start talking about resistances in series. Instead of just one resistance, we're going to talk about putting a few of them together in a circuit. All right, now we're going to take a look at resistances in series. Look at this circuit here. I have a source with some voltage VT, so the total voltage increase in this circuit is going to be right there, VT. And connected to this source, I have 1, 2, 3 resistances in series. They all come one right after the other. And you'll notice there's going to be a potential decrease or a voltage drop across each resistor. V1, V2, V3. Those are the potential decreases or the voltage drops across each resistor. Now, what are the characteristics of resistances in series? Well, first of all, you'll notice that they're going to have the same current in all of them. The current that's leaving the source, well, it's not going anywhere, right? That same current is going through every single one of those resistances. So that's the first characteristic of a bunch of things in series. The same current in all of them. How about all these voltages? Well, remember, in any circuit, the voltage increases are equal to the voltage decreases. The voltage increase through the source is going to equal the voltage decrease through the load, or the loads in this case. So you've got an increase of VT over here. Well, that increase is going to equal to all these decreases added together. So VT is going to be equal to, just like it says, V1 plus V2 plus V3 plus V4, and so on and so forth. If there's 100 resistors here, you're going to have 100 voltages over here. The total voltage increase equals the total voltage decrease. And last thing, imagine these were light bulbs. It would be impossible to turn one light bulb off, right? No matter where you put a switch in the circuit. Like if you put a switch in here and you open it up with the idea that you're going to try and turn that light bulb off, well, you're basically interrupting the flow of electrons through the whole circuit. Everything's going to go off. Doesn't matter where you put your switch. Okay, as soon as you open that switch up, the flow of current through the whole circuit is disrupted and everything everything goes off. So individual control of any one thing in the circuit is impossible. So those are the characteristics right there of a bunch of things in series. What we want to look at next is the equivalent resistance of all these resistances in series. Okay, now let's see if we can figure out what the equivalent resistance to these three things would be. In other words, if I took a circuit over here and I had the same source, but instead of having 1, 2, 3 small resistances, I had one bigger resistance that's equivalent to these 3. Well, how big would that equivalent resistance be? Okay, so what we're trying to figure out, okay, what's the total or equivalent resistance to these 3 smaller ones? Okay, well, it's kind of intuitive, right? The equivalent resistance to these 3 smaller ones is going to be, well, just the sum of all the smaller ones. Just add these up and there's the total or the equivalent resistance to them. It seems pretty intuitive. Let's prove it though. Sometimes, you know, things aren't always the way they seem to be. So let's just mathematically prove that, yeah, this is true. Okay, so we want to prove that the equivalent resistance to these 3 small ones is basically going to be equal to the sum of all those small resistances. Okay, if we're going to prove that, let's start off with something that we know for a fact. And what do we know about this circuit for a fact? Well, we know, remember, it's Kirchhoff's second law. The voltage increase is going to equal to the voltage decreases, right? The voltage increase, Vt, is going to equal to the voltage decreases. V1 plus V2 plus V3, and so on and so forth if there's even more resistances. Okay. Now, what can you do with this over here? Well, how about this? V1. Okay. The voltage drop across this resistor is going to equal to the current through it times the resistance itself. V1 is going to be equal to I times R1. How about V2? What's V2 equal to? Well, this is the voltage drop across this resistor. The voltage drop across the resistor is equal to the current through it times the resistance itself. You know, Ohm's law, V is equal to I times R. And you can do the same thing for V3. The voltage drop across the resistor is equal to the current through it times the resistance itself. And so on and so forth. If there was 100 resistances in the circuit, you could do this 100 times. Okay. How about Vt? What can we do about that? Well, look over here in the circuit where we have our equivalent resistance drawn. Vt is the total potential increase, so that's got to equal the total potential decrease on the other side through the load. So one more time, the voltage drop or the potential decrease through a resistor is equal to the current through the resistor. Vt is going to be equal to the current through the resistor times the resistance itself. And you can imagine what happens next. Look, in every single one of these terms, we have an I.
Please contact the office.
So you can divide both sides by I, and all the I's cancel. And yeah, you are left with the equivalent resistance is equal to the sum of all the resistances in series, however many there are. Draw a box around that and never forget it. We'll come right back and we'll do a little example, a problem where you're going to have to use some of these ideas. Here's a good problem to take a look at. 10 and 15 ohm resistances are connected in series to 120 volt source. Find the voltage drop across each resistor. So the first thing to do is to draw the circuit that you're dealing with. It might not be given. And if that was the case, here it is. 120 volt source connected in series to a 10 and 15 ohm resistor, and we want to find the voltage drop or the potential decrease across each resistor. Essentially, we want to figure out what V1 and V2 is. So tell you what, let's see if we can figure out what V1 is for starters. How can we do that? How about Ohm's law? Ohm's law is to electric circuits what F equals MA is to force problems. It is kind of the key to almost everything you need to know about electric circuits. So let's apply Ohm's law to this resistor right here. The voltage drop across the resistor, that's what we're interested in, right? Is going to be equal to the current through the resistor. I, we don't know what that is, but hopefully we can figure that out later. Times the resistance itself, which is 10 ohms. Okay, now, how can we figure out what I is? If we can figure out what I is, V1 is going to be a piece of cake. How about this? Suppose we treat these two resistances, suppose we lump them together and treat them as one big resistance. In other words, let's talk about the equivalent resistance to these two things. And that's easy enough to do, right? Two resistances in series, the equivalent resistance is just going to be them added together. Okay, so if we imagine these two resistances as one big resistance, there's the equivalent resistance, 25 ohms. Now, how about this? In any circuit, the potential increases are equal to the potential decreases. So you've got a potential increase of 120 volts on this side. That means through this one big resistor here, remember, we're treating these two things as one big resistor. The potential decrease across this one big resistor is going to be 120 volts. So the potential decrease or the voltage drop across the resistor is equal to the current through it times the resistance itself. And if we're treating these as one big resistance, that one big resistance is going to be 25 ohms. So you solve this equation for I, and what do you get? The 25 goes across the other side and goes downstairs. So that's going to be 120 divided by 25, that's like 4 and 20 left over, so 4 and 20 25ths, that's going to be 4.8 amps.
Mr. Cullen, please contact the office.
So now we're ready to figure out V1, the voltage drop across this resistor. It's going to be equal to the current, which is 4.8 amps, times the resistance itself, which is 10. You do the arithmetic, and there you go, 48 volts. So this voltage right here, 48 volts. Okay, so how can we figure out V2 now? Tell you what, there's 3 different ways to figure out V2. 3 different ways to figure out V2. Can you see what those 3 ways are? Of course, one way is just Ohm's law, right? The voltage drop across a resistor is going to be equal to the current through it, and we know that is 4.8 volts. Times the resistance itself. So you go 4.8 times 15, you do that on your calculator, and you're going to get 72 volts. What's another way to come up with that 72 volts? Even easier than multiplication. How about subtraction, right? How about subtraction? Look at this. The total voltage increase is 120 volts. So that means the total voltage decrease has got to be 120 volts. If you got an increase of 120 volts on this side, that means you got to have a decrease of 120 volts in total on this side. So 120 take away 48, well, there's another way to get your 72. What's a third way to figure out V2? There's actually a third way you can do it. That way's a little more subtle. It would work something like this. Remember, for either of these resistances, the voltage is going to be equal to the current times the resistance. Okay? Doesn't matter which one of these resistances you're talking about, the voltage is going to be the current times the resistance. But in both cases, the current is the same thing. The current is a constant. So look at this. No matter which resistance you're talking about, the voltage is going to be some constant times the resistance. The voltage and the resistance are proportional to each other. So in other words, to figure out this voltage, because things are proportional, you can write ratios. Okay? Watch this. Watch this. I'm going to say this voltage is to this voltage. As this resistance is to this resistance, because the voltage and the resistance are proportional. You can write ratios involving them. So this voltage is to this voltage as this resistance is to this resistance. And if you solve this equation, you take the 48 over the other side, it goes upstairs. You're going to get your 72 volts that way. That's the beauty of these circuit problems, is that you can figure out your answers more than one way. And I encourage you to do that. You wouldn't have to do it all three ways, but at least do it a couple different ways. Make sure you get the same answer both times, and then you know you got it right. Okay, you are now ready to tackle an assignment on this. It will be posted along with the video. Good luck, and we will see you again tomorrow. Tomorrow we're going to take a look at parallel circuits. Bye for now.